So for this lecture, we will discuss several topologies on the dual space. So let us consider a Banach space. And X prime be its dual. So we have the strong topology of the dual space. And this is, or this will be denoted by Px prime S. So this is the metric topology. Generated by this distance function induced by the dual norm. Okay, and we know that if X is a Banach space, then X prime is also a Banach space. In fact, completeness in X is not needed because the range here is the set of real numbers, and we know that the set of real numbers is complete. X prime and Y prime lies in the dual space. Next, we have the weak topology of X prime. So similar to the weak topology in X, we denote this by a sigma X prime, X double prime. So that's the bidual. And this is the topology generated by the elements of the bidual space. There's another topology, and we call this the weak star topology of X prime. The notation would be sigma X prime X. So here, the notation for the weak topology in X is reversed. Okay. In other words, the order of the spaces here. And this is the topology generated by the images of the canonical embedding from X to the bidual space. So J is a mapping from X to its bidual. This is the canonical embedding that we discussed in the previous lecture. And we know that this is a linear isometry, hence 1-to-1. And based on these definitions, it follows that so similar to the weak topology in X. So the weak topology in the dual space is contained in the strong topology. However, the weak topology is larger than the weak star topology. Well, this follows, the first inclusion follows easily from the fact that this collection of functions in the dual space, or it is contained in the bidual space. Okay. So in other words, the weak star topology utilizes fewer functions. Okay, therefore, you have fewer open sets. So let us again consider the following question. Let's start with the weak topology. Okay. And also the equality between weak star and weak topologies on X prime. So don't be confused. The first argument here is the set wherein we assign the topology. The second corresponds to the functions that is utilized. So for the weak topology, we use the bounded linear functionals in the dual space. And for the weak star topology, well, by identifying X with the image under the canonical embedding, that's how the weak star topology is constructed. So for this lecture, we will concentrate on the first question. The second one will be on the succeeding lecture. So to answer the first one, and you might guess already that this is valid if and only if X is finite dimensional. First, we start with the following lemma. A Banach space is finite dimensional if and only if its dual is also finite dimensional. So let us look at the proof. Suppose that X is finite dimensional. Then utilizing our strategy before, so going back to our proof. So we can take a basis for this function and then construct the coordinate functions. The coordinate functions you can show that these coordinate functions with respect to some basis of X form a basis of the dual space. Since the coordinate functions has the same dimension or has the same number of elements with the dimension of X, so the dimension of X prime is the same as the dimension of X. And we know that this is finite. Okay, now suppose that the dimension of the dual space is finite from this implication. We know that the dual, the dimension of the dual space, that's the bidual, is finite. Since the canonical embedding is injective, so one-to-one, in general, the dimension of the bidual can be larger than X. But what we know is that the dimension of X is the same as the dimension of the image. And this is less than the dimension of your dual space. Hence, the dimension of X is also finite. Based on this simple observation, we can now answer this question here. So the weak topology on the dual space and the strong topology are equal if X is finite dimensional. And that is the content of the following theorem. So for completeness, let us present the proof. So recall that these two equal if and only if, according to our previous theorem, when we replace x by x prime, if and only if the dual space is finite dimensional. But this is true if and only if the dimension of x is finite, according to the previous theorem. And that's the proof. Okay. And we will leave this in the succeeding lecture. So analogous to the case of the weak topology, we can also introduce a neighborhood base for the weak star topology and discuss or introduce the notions of weakly star convergent sequences. Okay. So the following theorems are similar to the case of the weak topology. Therefore, we do not provide the proofs, and let us just state them. Given a bounded linear function of x naught prime in the dual space, a sequence of functions in the Banach space, and a positive number r, let us define the following set: V of x naught prime define a sequence and the number r. So this is the set of all elements in the dual space wherein this duality pairing the magnitude is less than r for all j from 1 to k. Take note that this quantity here, according to the definition of the canonical embedding, this is the same as what the duality pairing of x prime minus x prime naught, and the image of x sub j with respect to the embedding j sub x. So this is now a duality pairing in x prime and x double prime. Okay. And this is precisely these maps that defines the weak star topology. So with this notation, we have the following theorem. So let's say we have a Banach space X. And an element of the dual space. Then, if we form the collections of these open sets, okay, so I would emphasize here that this one is an element of the weak star topology. So J, K, J from 1 to K are such that this is a subset of X, R is positive and K is a positive integer. Then this one forms a neighborhood base at X star or at X naught prime with respect to the weak star topology. So again, the proof is almost the same. You just interchange the roles of X and X prime in the previous discussions. Also, if we take, let's say, a sequence in the dual space and an element X prime, also in the dual space, we say that the sequence converges weakly star, okay, to X if you have convergence with respect to the weak star topology. So the convergence is given by this pair of topological, by this pair corresponding to the weak star topology. And similar to the notation for weak convergence, we also use the following notation, but okay, to emphasize that this is with respect to the weak star topology, we put a star at the top of this notation. And by adapting similar arguments, we can prove the following theorem. So if X is a Banach space, I have a sequence in X and a sequence in the dual space. So here we also have four statements. The first one, weak star convergence is valid if and only if these duality pairings tends to this for all X in your Banach space. And again, this follows immediately from the definition of weak star topology and using the canonical embedding from X into its bidual. Strong convergence implies weak convergence, or more precisely, weak star convergence. And a weakly star convergent sequence is also bounded with respect to the dual norm, and the norm functional corresponding to the dual norm is weakly star sequentially compact, as sequentially continuous, I should say. And finally, if you have the following convergence, suppose I have a weak star convergence and a strong convergence in X. This implies that the corresponding duality pairings also converge to the duality pairings of the limit. So the proof are very similar to the previous theorem. You just interchange the roles of X and X prime in the previous discussions. So to discuss further properties of weak star topologies, let me state the following theorem without proof. This is called the Banach Alaoglu theorem, or sometimes they call this the Banach Alaoglu Bourbaki theorem. If X is a Banach space, then the unit ball in the dual space, so again this is the space of all elements in the dual space having dual norm less than 1, less than or equal to 1, okay? Then the unit ball in X prime is compact with respect to the weak star topology. In other words, we say that it is weakly star compact. Take note that compactness depends on the topology or the open sets involved. So you need to specify here what is the corresponding topology. So again, here the topology should be in X prime because this is a subset of the dual space. So in a Banach space, the closed unit ball is not compact in the weak topology in general, but it is compact with respect to the weak star topology. So the proof here utilizes, let's say, the Tikhonov theorem, which states that the product, it can be an arbitrary product, of compact sets is again compact. So the idea is to rewrite this unit ball as an arbitrary product of compact sets, and by applying Tikhonov theorem, that would imply the compactness of the closed unit ball with respect to the weak star topology. And there's another, of course, way of characterizing compactness. So instead of talking about open sets or open covering, we can characterize compactness through nets. Okay, and nets are somehow you can think of them as generalized sequences. Okay. Well, the problem here is that the weak and weak star topology are not necessarily metrizable. So compactness and sequential compactness must be distinguished. So I will not provide the proof. You may, for instance, refer to the book of Danford and Schwartz. Using this Banach-Alaoglu theorem, there's a result called the Eberlein-Smulian theorem. Which characterizes weakly compact sets. So if we have, let's say, a Banach space X and a subset K and X. So even though the weak topology is not metrizable, we can characterize compactness in the weak topology by weakly sequential compactness. So we say that a K is weakly compact so in other words, compact with respect to the weak topology on X if and only if every sequence in K has a weakly convergent subsequence. And the limit must be NK. And this one uses the Banach-Alaoglu theorem. Or the Banach-Alaoglu theorem can be utilized to prove this result by Eberlein and Smulian. So again, compactness and sequential compactness are equivalent in the weak topology of a given Banach space. Even though the weak topology is not metrizable, this result is still valid. Okay, so these are compactness results with respect to the weak star topology and then the weak topology for general Banach spaces. To prove other results, let's say we add additional structure on our Banach space, namely the existence of a countable dense subset. Or in other words, we now assume that our Banach space is separable. So adding separability, we can prove a version of the Banach-Alaoglu theorem for separable Banach spaces. Okay. So on a separable Banach space, the closed unit ball in X prime is weakly star sequentially compact. So this is more compared to the Banach-Alaoglu theorem, or because instead of compactness, we have a sequential compactness with respect to the weak star topology. And the basic idea is to construct a subsequence, okay, on the closed unit ball that is convergent with respect to the weakly star topology, and using the dense subset of the Banach space. And let us go to the details of the proof. So as a first step, let us consider, okay, so our general assumption here. So consider a sequence in the closed unit ball in X prime. We want to show that this has a subsequence that converges weakly star to some element in the closed unit ball. By a separability, we can take a set D. Okay, let's say this is a DM. Okay, B dense in X. Again, this is guaranteed due to the separability. Now, let's start with the estimation of this duality pairing. This is less or equal to the norm of D1 times the dual norm of Xn. However, Xn prime lies in the closed unit ball. So the norm of this is less or equal to 1. Hence, this product is less than or equal to the norm of D1X. Of course, these are real numbers. So we have a bounded sequence of real numbers. We can apply, let's say, the Heine-Borel theorem. stating that a bounded sequence in R has a convergent subsequence. And let us call that X1n. Of your original sequence, and a limit. Let's call this LD1, the limit, such that when applied to the subsequence, we have convergence with respect to this limit LD1. Okay. So here we emphasize D1 because a different element of the dense subset may produce a different limit. And at the same time, this limit should be bounded above by the same bound of your sequence. On a similar note, okay, let us apply it now to the case of D2. But instead of the whole sequence, we take the subsequence. And again, this is less than the norm of dx. D2, the norm of D2 in X. Thus, again, the Heine-Borel theorem implies the existence of a subsequence x2n prime of x1n prime such that okay, d2 x2n prime, this duality pairing tends to LD2. Okay, what is LD2? This is the limit. And that at the norm of the limit is less or equal to the, or the magnitude of the limit is less than or equal to the norm of D2. In particular, D1, x1n prime, okay, since this is a subsequence of x1n prime, we have the convergence of this, okay? So if you take a subsequence, namely x2n prime, you still have convergence to LD1. So we continue this process. So by induction, so given a positive integer m, there exists a nested subsequence so let us call that what xmn prime. So you have here up to the first process. These are all subsequences of your original sequence such that let's say d sub j xk n prime. This one tends to LDJ for all j from 1 to m. And for k less than or equal to j. Okay. And let us write it in this way. And similarly, this is less than or equal to the norm of L d, or the norm of dx, dj and x. So you construct a nested subsequence wherein you have this property. We now go to the second step. We apply a diagonalization. So let us denote by x tilde n prime this term, okay, or this bounded linear functional. Okay. Then since our process only generates a subsequence of your original sequence, so this must be also in the closed unit ball and x prime. And at the same time, the limit of this by construction, we should say n tends to L d j. And we take here j to be equal to n. So here you take j to be n and k to be n. And moreover, this must be valid for all n. So we applied some sort of a diagonalization argument. So therefore, we have a map. So this defines a map L from the dense subset into R as follows. Okay. So this would be the definition of our map L dn. Okay. Now we extend, okay, this to a linear map on the span of D as follows. So L, so let us denote the extension by capital L. So L of an element of the linear span, and it is of this form. We define this to be the linear combination of the corresponding images. Now, for every y in the linear span of the dense subset by linearity, okay, so you use this and apply a linearity. We know that this duality pairing there is an error here. There should be d sub j. Okay, and this must be j. So if you apply a linearity and assuming that, let's say y has this representation, a generic element of the linear span. So this one is equal to the following linear combination. Okay. Not to be confused with the index or indices. Let us use a different index here. Let's say n. Okay. So according to linearity, this is alpha j. A duality pairing of dj x tilde n prime. Okay. And this tends to L dj. Okay, according to this limit here. Therefore, this is equal to L of y. Or let's say Ly, since this is a linear map. And moreover, you can see that the magnitude of Ly, and this is what the magnitude of let's say the limit of the magnitude of this. Okay. But this is less or equal to, okay. We can extend this property, okay, to the case of y. Indeed, you just apply the linearity of this duality pairing. And let's do that for clarity. So let's say this is what L of alpha j dj, and this is what less or equal to, applying the triangle inequality, and the norm of L dj. There must be an absolute value there, times okay, going back to this estimate, I think there's another easier way without passing to the linear combination. You can, of course, bound this by the following. So this is less or equal to y norm of x, norm of y and x, and then the dual norm. But since the dual norm is of xn tilde prime is less than 1, you have this property. And let's move this a bit to the right. Okay, so that's boundedness of L. So we can now extend, okay, by the density since D is dense in X, okay, we also have the closure, okay, of the linear span is also X. Well, what you can observe that, of course, the span is larger than the set. The closure of the larger set is larger, so you have this. And this is a subset of X. Okay, so therefore you have equality. We have an extension of L now on X. So instead of the linear span, we take the closure of it, which is X. And it is defined as follows. So Lx is the limit as n goes to infinity of Lxn, or I should say Lyn. And here the limit is taken in R, okay? And Yn is an element of the span of D, and Yn tends to X, strongly in capital X. This extension is unique. I mean, yes, it's unique due to density, and you can prove that it is linear and bounded. Okay. And the details, I will leave that for you to verify. So with this process, we now have bounded linear operator with norm less than 1. And what is that? And why is that? Due to this estimate here. Okay, now we show that, okay, as the final step, we show that this is the required subsequence and it converges weakly star to this limit L. So we apply here the definition of the weak star convergence, peak an X in capital X, and an epsilon that is greater than 0. We can find a D, okay, that depends on epsilon and X, okay, according to the density that is close enough to X. In other words, the distance between the two is less than epsilon. Okay, then let us compute this difference of duality pairings. If we can establish that this the limit of this is 0, then we are done. So by linearity, this is x and tilde prime minus L. We apply the triangle inequality, add and subtract minus d. So we have here d of x and tilde prime minus ld. This is less than or equal to 2 epsilon. Okay. And why is that? Of course, you can write this as, or you can estimate this as follows. Here you apply the triangle inequality. And we know that this is less or equal to 1. And similarly for this one. And this is less than epsilon. So therefore, you have less than 2 epsilon plus the second term. And we know that this, let's say, that there exists for some m depending on d. Okay. Hence, this depends on epsilon and x, a positive integer, such that, okay, this is less than epsilon for all n in capital N. And why is this the case? Okay, so we should correct this. N greater or equal to m. Going back to our discussion, we have this convergence here. So this convergence holds for any element and the dense subset. So therefore, you have this also. So we need to rescale. So let's say this is epsilon by epsilon over 3. Okay. Thus, if you combine the two, you now have if n is greater or equal to m, then this difference of duality pairings is less than epsilon. And this proves convergence of your subsequence into L. And that completes the proof of this special case of the Banach-Alaoglu theorem. But the weak compactness is replaced by weak sequential compactness, again with respect to the weak star topology. So let us discuss an immediate consequence of this. Okay. So let X be a Banach space. And let's say I have a sequence in the dual space. that is bounded. Then there exists a subsequence x and j, okay, and an x prime, okay, the dual space, such that this subsequence converges weakly star to x prime. The proof is simple. You just need to scale this. So suppose that M is the bound for your sequence. Dividing by M, okay. You obtained a sequence in the closed unit ball in X prime. Okay, so there is a subsequence. A subsequence exists such that xn prime over m converges weakly star to some y prime. Okay, for some y prime in bx prime. Then you can now see that this implies multiplying by m, and you can show that, okay, that weak star convergence is invariant under scaling. So xn prime converges weakly star to m y prime, and you may take this as your x prime. Okay, and of course here I need to add separability. So a separable Banach space. So again, a bounded sequence in the dual space of a separable Banach space has a weakly star convergent subsequence. So in the following example, let us characterize weak star convergence with respect to some concrete function spaces. Let's start with the Lebesgue spaces. Take a measurable subset omega with respect to the Lebesgue measure. And let's say, so for p less than infinity but greater or equal to 1, if we apply the Ries-Fischer theorem, that is the fact that LP omega is isometrically isomorphic to, let's say, LQ, where Q is the dual of P. Then we have, okay, of course, we can interchange the roles of P and Q, and we have this. I think this is the statement because P is should be the one that is less than infinity. Okay. Then in this case, we have the convergence or the weak convergence. So Fj converges weakly to F in LP if and only if the integral of let's say Fj g dx tends to this. Take note that this is the isometric isomorphism from dual of LP to LQ. In the case of P equal to infinity, we know that the dual of L1 is L infinity. So L infinity is the dual of L1. We do not use the Riesz-Fischer theorem directly, okay? But here we use a different convergence. So instead of weak convergence, we have weak star convergence. So this is valid if and only if, okay, still have the same convergence, but now for all G and L1. And this follows from the definition of the weak star topology. Okay, so that's the first example. In the context of, let's say, Sobolev spaces, so let us consider an open set. Then in the case that P is finite, you have the weak convergence of Fj and F and WKP. K is a positive integer. If and only if the weak derivatives converges weakly, okay, in LP. For every alpha with length less than or equal to k. And for this weak convergence, you apply the first property here, and you do that for every weak derivatives. So let us put the general assumption that k a positive integer in this case. And if p is infinity, then similarly, you have weak star convergence in wk infinity. If and only if your weak derivatives converges weakly star to the weak derivative of the weak star limit in L infinity. And finally, if let's say K is compact, Then we have, let's see, the weak star convergence of regular countably additive measures, Borel measures, and K. So according to the Riesz-Radon theorem, this one is the dual of CK prime. Okay. Then this is true if and only if the integral over K of let's say F under with respect to the measure mu sub J tends to the integral over K of F with respect to the weak star limit measure. This is true, or this must be true for all F in CK. So applying the Riesz-Radon theorem, we can characterize the weak star compactness or weak star sequential compactness in RCA of K. So all of these examples just they follows basically on the various theorems, duality theorems that we discussed in the previous lectures, along with the definition of weak and weak star topologies. So in the next lecture, we will be concerned in the case where the weak and weak star topologies are equal.